Hello and welcome again. I am Sachidanand Prasad, and today we will be discussing a problem on real analysis. This is a problem in a series of daily problems. So the problem is discuss the differentiability of the function given by this, that f of xy is equals to x cube plus y4 by x square plus y square if xy is not equals to 0 and 0 if xy equals to 0. We will solve this problem by two methods. The first method involves by computing the directional derivative, and the second method involves by seeing the linearization of this function. So let's head to the solution. So I encourage you to pause this video before seeing the solution and try with your own. Okay, so I hope you have tried to solve this problem. So let's see the solution. So if you see the problem, then the problem is to understand whether or not this function is differentiable at the point 0, 0. Because you see that at rest of the points, because this is a polynomial, this is a polynomial, and this is also a polynomial, and so this function is like p by q, and apart from 0, 0, q is always non-zero, and therefore this function is differentiable apart from 0, 0. So that's why the only problem is to understand whether or not this function is differentiable at point 0, 0. Okay. So if the given function is differentiable at 0, 0, then it must be linear, because we know that the derivative of a function is a linear map, and hence all the directional derivative will also be linear. Okay. So what we will do, we will compute the directional derivative and we'll see whether it's linear or not. So recall that the directional derivative at a point x in the direction v is given by dfxv is so this is the notation for the directional derivative of f at point x in the direction of v. So this is limit t tends to 0, f of x, this is f of x plus tv minus f of x by t. Okay. So I'll emphasize here that if the directional derivative is linear, then we cannot conclude that the function is differentiable. But if it is not linear, then we can say that the function is not differentiable. Okay. So this is the formula for the directional derivative. So let's compute this limit and see whether the directional derivative is linear or not. So if I represent v as v1, v2, then df0v is what? Limit t tends to 0. So what is this? F of 0, 0 plus tv, which is same as f of tv minus f of 0, 0, this by t. Okay. So what was the function? So the function was x cube plus y to the 4 by x square plus y square. This if xy was non-zero, and 0 if xy was 0. So what is the value at tv? So its tv is nothing but tv1 comma tv2. So if I substitute, then x cube will be t cube v1 cube plus y4 is t4 v2 to the 4, and in the below we have t square v1 square plus t square v2 square, and f00 is 0 by t. Okay. Now, so what is this? So this is nothing but, so I can write this as this thing. I can write t, I can take t cube as common, so t cube times v1 cube plus v2 to the 4 times t by, and this t will be get multiplied, so I'll be getting t cube times v1 square plus v2 square. Okay, and hence I can cancel this t cube and t cube to remain this thing. Okay, and therefore we have this that limit t tends to 0, v1 cube plus t times v2 to the 4 by v1 square plus v2 square. But what is this limit? This t will be get 0, and hence this limit is v1 cube by v1 square plus v2 square. And clearly this function is not linear in terms of v1 and v2. Okay, so this is not linear, and hence the given function is not differentiable at 0. So no, I will again make a remark here that not linear will implies that not differentiable, whereas linear will may not imply differentiable. So it may happen that all the directional derivative exists and they're linear, but the function is not differentiable. Okay, so let's see the second method to solve this problem, and this is a more general method. So another way to tackle this problem is to see the linear approximation of f at 0, 0. So what do I mean by the linear approximation? So the linear approximation of the function is given by the point f00 plus x times. So how this is coming? So basically what we write the Taylor series of the function f of xy around this point. Okay, so this is like f00 plus the x times this, okay, and plus the higher order terms. Okay, so the linear approximation is basically this thing. This is the linear approximation. Okay, because the other terms are higher degree terms. Okay, so note that. So let's compute what is this and this. So what is the del f by del x at 0, 0? So in the previous computation, we have shown that the directional derivative in the direction of v1, v2 was v1 cube by v1 square plus v2 square. Now here, what is v? So if I am taking del f by del x, then v1 is 1 and v2 is 0. So I am 1, 0. So if I'll put 1, 0, I'll be getting 1. Okay, and the del f by del y will be 0. Okay, so this means that what is the linear approximation? This is equals to 0, this is equals to 0, and this is equals to 1. So the linear approximation is x. Okay, fine. So now, so for f to be differentiable at 0, 0, what we need that this limit should be equals to 0. Why this limit should be equals to 0? Because if the function is differentiable, then what we know that the higher order terms in the limiting thing, this in the limiting sense will go to 0. Okay, so therefore the only term that will survive is the linear approximation, because that is the function. Okay, that is the function. Okay, so this limit has to be 0. Okay, so let's compute this limit. So what is f of xy minus lxy? So this is f of xy was x cube plus y4 by x square plus y square, and lxy was x. So I have just substituted the value of f of xy and lxy. Now we simplify this. Simplifying this will give me x cube plus y4 minus x cube minus y square x divided by x square plus y square to the power 3 by 2. Now this x cube and x cube will be cancelled out, and what is this? This is y4 minus y square x divided by x square plus y square to the 3 by 2. So what I will show that this limit will not exist, because if this limit does not exist, then we can conclude that the function is not differentiable at 0, 0. So the above limit does not exist. So how do I show that? So for that, we take the limit along the curve y equals to mx. So see, if this limit exists, if this limit exists, then the value of limit should be same along all curves. All curves. Okay. So it means that if I take y is equals to some curve f of x, and then if the limit value is L, then if I take y equals to gx, then also the limit value should be L. So now I am taking the curve as y equals to mx. So y equals to x, y equals to 2x, y equals to 3x. For all these values, the limit should be same. Okay, so let's see at y equals to mx what is the value. So we were trying to compute this limit. So by substituting y equals to mx, so if you substitute y equals to mx, then the limit, this will change because xy tends to 0. It means that if x tends to 0, then y will automatically tends to 0. So this limit changes to limit x tends to 0. And instead of y to the 4, I'll be noting m to the power 4, x to the power 4 minus y square is m square, x square times x is x cube, and here x square plus y square will be this thing. Okay. Now, after simplifying this, I can just take x cube m square common out, and here m square minus 1 will be left, and here x cube will be, so I can take out x square. So from this, I take x square 1 plus m square and the whole to the power 3 by 2. Now what is this? If I'll open this, I'll be getting x cube times 1 plus m square to the power 3 by 2. And this is what this is. Okay. Now x cube will be cancelled out, and I'm getting m square times m square minus 1 by m square plus 1 to the power 3 by 2. Now you see that this depends on m. So it means that if I'll change the value of m, the value of the limit is changing, and therefore the limit does not exist. Okay, and hence the function is not differentiable at 0, 0. So what we saw is two methods to check whether the function is differentiable or not. One of the method was to compute the directional derivative and see if it is linear or not. If it is not linear at that point, then we say that then we conclude that the function is not differentiable. But if the directional derivative is linear, then that procedure is inconclusive. The second method is to see the linear approximation of the function and compute the limit of that f minus the linear approximation divided by x square plus y square with limit xy tends to 0, 0. So we compute this limit, and if it is 0, or then we are fine, but this limit does not exist here, and hence we conclude that the function is not differentiable. Okay, so I hope you have understood the solution of this problem, and we will see again tomorrow for a problem in complex analysis. Thank you for your time.